Okay, here we are, chapter 7.2, solving equations with addition and subtraction. This is an interesting process that we have going, and some of you already know how to do this, but just bear with me. We have to make sure we understand exactly what the book is trying to show us. For instance, most of us can see that if we have x plus 3 equals 4, we can see, without really doing anything, that x has to be equal to 1. Because 1 plus 3 is 4. So if x is equal to 1, that makes this all work. And we're going to have a lot of problems where you can see the answer right away, and you have to understand that it's important to me and to your education for you to do the method that I'm doing. I need you to understand what we're doing here. The solution is what this is. We're looking for solutions, but we need you to show your work in exactly the right way. Otherwise, you won't be learning what you need to learn. And you can see the answer quickly. I know that the solution will not be tough for you to find, but showing your work might be. So please pay attention to how to show your work. We're going to use what's called an inverse operation. Okay. Okay, an inverse operation is sort of undoing the operation that you might have done. So if you're adding, the inverse to adding is to subtract. If you're subtracting, the inverse is to add. And the same with multiplication. The inverse of multiplication is to divide, but we're not going to do that today. The inverse of division is to multiply. So these are inverses to each other, and these are inverses to each other, like opposites. And so what we're going to do is we're going to see that if we have this same problem, x plus 3 equals 4, what we're going to do is we're going to do the inverse operation. We're going to subtract 3 from 3, and we're going to subtract 3 from 4. And 3 take away 3 is 0. So we can just kind of get rid of that. That leaves x. And 4 take away 3 is 1, and that leaves our solution. So you see how we got the right solution, but we used a method, and that's called using the inverse operations. And please remember that when we have an equation, remember we talked about this last time, it's whatever's on one side of the equation, one side of an equal sign, and whatever's on the other side of the equal sign. They have to be equal. So, and it doesn't really matter if you have 3 on this side and you have y plus 1 on this side, then whatever y is has to add up with 1 to equal whatever's on this side of the equation. They have to match. And we like to sometimes think about it like a balance scale. The book uses a balance scale. Sometimes I use a teeter-totter because it's easy to draw. And I know we don't have as many of those in the playgrounds as we used to, but you have two sides of a teeter-totter. And if everything on this side is equal to everything on this side, then it's balanced and the teeter-totter holds flat. But if you put more weight on one side, it tends to drip, and you have to do the same to the other. So if we were to put this same equation on the teeter-totter, y plus 1 on one side and 3 on the other side, and this 1, see, this is a teeter-totter. It's like there's 3 people on this teeter-totter, and there's y plus 1 people on this side of the teeter-totter. We don't really know what y is, even though we can tell really easily that y is 2, because 2 plus 1 is 3. But we don't really know. So what we're going to ask this guy to jump off the teeter-totter. He's jumping off. That's kind of like subtracting 1. The opposite, the inverse operation of adding 1 is to subtract 1. And if we do that, it's no longer balanced. So we have to subtract 1 person from this side. And when we do that, now we have a teeter-totter that's still balanced. When we take 3 away, or 1 away, now there's 2 people on this side. And there's y on this side. And we can see that if it's still balanced, which it should be, that y and 2 have to be the same. And they must be equal. So y is equal to 2. Now we already knew that. But you have to follow the process through. You just have to keep doing it. So we have to do this, and we do the inverse operation for everything. If they give us a different problem, say x take away 4 is 5, or is equals 5, and we can imagine this teeter-totter, and we just are simply going to write Well, the inverse to subtract 4 is to add 4. If we take 4 away and we add 4, we really have the same amount that we started with. Say I have 5 and I take away 4, that's 1, and I add 4, that's 5 again. And so these two cancel each other out. But to keep our balanced, our teeter-totter balanced, we have to do the same thing to the other side. We have to add 4 also. And when we add 4 to 5, we get 9. So x is equal to 9. It's like adding 4 people on this side of the teeter-totter and adding 4 people to this side of the teeter-totter just to keep it even. And now we can see, with only x left and 9 people on this other side, that we get an answer that makes sense. So we're always going to solve it using this method. Always have to do it. And so far we're just adding and subtracting. Okay, so it doesn't appear like it's going to be too hard. X plus 2 equals 9. So I have to do the inverse. So this is add, so I'm going to subtract 2. 2 plus 2 take away 2 just leaves me x. And I could say x plus 0, but that's sort of, x plus 0 is just x. And when I subtract 2 from this side, 9 take away 2 is 7. So x is 7. And this is my solution. Okay? And you just keep going just like this. Sometimes they'll write it the other way, and so you have to be ready for that. 26 is equal to 11 plus x. It's one reason that we stop using x as a time symbol. Plus is almost confusing. You got to make sure you write it correctly. Ooh, that green is too bright. Okay, so we're adding x. Now this is a little confusing because it doesn't look like we're adding x to 11, but really this is like a positive 11, and we're going to get into positive and negative numbers or integers. But right now the way to get rid of 11 is to subtract 11. So that leaves us with 0 plus x. It leaves x all by itself over here. And then we have to subtract 11 from the 26, and that leaves us 15. So x has to be 15, and we can put it back in the equation. 26 equals 11 plus x, and we decided that 15 is equal to x, which means x is equal to 15. So if we put 15 in here and we add those together, it does equal 26. We can see that we're right. So x is 15. So it doesn't matter if they put it forward or backwards, we can do it. In fact, we could even change places. This equation could be written 11 plus x equals 26, because it doesn't matter. Everything on this side is equal to everything on this side, and if they change sides, they're still equal. So here we had 26 plus 11, or equals 11 plus x. Now we have 11 plus x equals 21. And then remember the commutative property, that's an important one. In addition, we can actually change these around. So we change the 11 and the x around using the commutative property. So this still works. Now over here I didn't do any of that, I just subtracted 11. Okay, and that's fine for you to do, but I wanted to show you what's happening there. It's really okay, because if I subtract 11, I'm still doing the same thing. X equals 15. Okay, very good. Hopefully that wasn't confusing. It could have been. That's how this lesson goes. All right.